Welcome to the sixth Introduction to Real Analysis lecture. The topics that we will explore in this lecture include the well-ordering property of the natural numbers, the algebraic structure of the natural numbers, the integers, and the rational numbers. Okay, so we'll start this lecture with the exercise from the previous lecture, and we'll prove it as a theorem. Let f be a function from a into b, and g be a function from b into c. Then the inverse of the composition g of f is the composition f inverse of g inverse. So proof. Now since f and g are both bijections, the composition g of f is also a bijection. And so it has an inverse. And that inverse is a function from c into a given by the inverse of g of f is the set of ordered pairs CA and the Cartesian product C cross A, such that the ordered pair AC is in the composition G of F. Now also, since F and G are both bijections, these functions have inverses. F inverse, which is a function from B into A, and G inverse, which is a function from C into B. And so the composition F inverse of G inverse is the set of all ordered pairs CA in the Cartesian product C cross A, such that there exists an element B in the set B such that G inverse of C is equal to B and F inverse of B is equal to A. So we have two sets. We need to show that they are equal. So let the ordered pair CA be in the inverse of the composition G of F. Then the ordered pair AC is in the composition G of F. And so there exists an element B in the set B such that F of A is equal to B and G of B is equal to C. Now as F of A is equal to B, F inverse of B is equal to A, and as G of B is equal to C, G inverse of C is equal to B. And so there exists an element B in the set B such that G inverse of the element C is the element B, and F inverse of the element B is the element A. This is the condition for the ordered pair CA to be in the composition F inverse of G inverse. That is, if the ordered pair CA is in the inverse of G of F, then this implies that the ordered pair CA is in the composition F inverse of G inverse. And hence, the inverse of the composition G of F is a subset of the composition F inverse of G inverse. So conversely, let the ordered pair CA be in the composition F inverse of G inverse. Then there exists an element B in the set B such that G inverse of C is equal to B and F inverse of B is equal to A. So as G inverse of C is equal to B, we have that G of B is equal to C. And as F inverse of B is equal to A, we have that F of A is equal to B. And so there exists an element B in the set B such that F of A is equal to B and G of B is equal to C. This is the condition for which the ordered pair AC is in the composition G of F. And if the ordered pair AC is in the composition G of F, then the ordered pair CA is in the inverse of the composition G of F. That is, if the ordered pair CA is in the composition F inverse of G inverse, then this implies that the ordered pair CA is in the inverse of the composition G of F. So we have demonstrated set inclusion in both directions, and so the sets are equal. The inverse of G of F is F inverse of G inverse. So next, we'll prove what is known as the well-ordering principle of the natural numbers. And the statement of that principle is if S is a non-empty subset of the natural numbers, then there exists an element M in the set S such that M is less than or equal to K for every element K in the set S. In other words, if S is a non-empty subset of the natural numbers, then S has a least element. So proof, let S be a non-empty subset of the natural numbers. Now for a contradiction, assume that the set S has no least element. We will show that if S has no least element, then S must be the empty set, which is a contradiction. So let the set T be the complement of the set S in the natural numbers. Now, if the number 1 were in the set S, it would be the least element. Since 1 is the least element of the natural numbers. But since S has no least element, 1 is not in the set S, and so 1 must be in the complement of S in the natural numbers, so 1 must be in the set T. So now suppose that for some natural number k, 1, 2, and so on, in increments of 1 up to the natural number k is in or are in the set T, then if the successor of k, which is k plus 1, were in the set S, then it would be the least element. Since all natural numbers less than k plus 1 are in the set T. But again, as the set S has no least element, k plus 1 is not in the set S, and if it is not in the set S, it must be in the complement, and so k plus 1 is in the set T. That is, the number 1 is in the set T, and if k is in the set T, then this implies that k plus 1 is in the set T. And so by the principle of mathematical induction, the set T is the entire set of natural numbers. And since we now have that the set of natural numbers is equal to the set of natural numbers set minus set S, S must be the empty set, which is a contradiction or which contradicts our original hypothesis. And therefore, by contradiction, if S is a non-empty subset of the natural numbers, then it has a least element, and so there exists an element M in the set S such that M is less than or equal to K for every element K in the set S. Okay, so I'd like to take a moment to talk about the number 0. The ancient civilizations did not recognize the concept of the number 0, Instead, they recognized the concept of the absence of a number, and some of these ancient civilizations had a symbol for the absence of a number, and that was most prominent in civilizations that had a positional number system. So first, let's look at a semi-positional system, which was the Roman system. So we'll look at the Roman numerals. A numeral is a symbol for a number, and for the Roman numerals, for the first three, we essentially have a one-to-one correspondence between hash marks and the numbers. But beginning with the number, the numeral for the number 4, we have, this is where position comes in. We position a number less than one that precedes it, or one that follows it rather, v, to give one less than the numeral v, which is the numeral for the number 5. And then we build upon v until once again we position a numeral less than the one that follows it to indicate one less than the numeral, one less than the number represented by the numeral x, which is 10. And the Romans also had a separate symbol, separate numeral for the number 100. So now let's compare that to the system that we in the West inherited, the Hindu-Arabic system, which is a true positional system based on powers of 10. And in the Hindu-Arabic system, there are distinct numerals for the first 9 digits, 9 numbers. And I'm going to use the Western version of those numerals rather than the Hindu or the Arabic. But then to represent the number 10, there we use a positional notation of a dash or a dot to indicate that there is no unit value. Instead, we have one of the 10 to the power of 1 value. And similarly, for 100, it was originally represented as 1 followed by 2 dots or 2 hash marks, which indicated that there were no units, and there were also no multiples of the of 10 to the first power, but there is one multiple of 10 to the second power. So it wasn't until the year 628 in the Common Era that the Indian mathematician slash astronomer Brahmagupta, who was born around 598 in the Common Era, published the Brahma-Sputa Siddhanta. Now, the Siddhantas were the traditional astronomical texts of the school of the Brahmas, and the word Sputa means accurate or corrected, and so this title basically means a corrected Siddhanta of the school of the Brahmas. And in this text, number is the 0 is a number rather that can be used in arithmetic, and 0 is the number such that a plus 0 is the number a for every number a. Now, when we have a concept of 0 as a number, we also have a concept of positive and negative numbers. And so positive numbers are the numbers greater than 0, and negative numbers are the numbers less than 0. Now, these concepts transferred well into China and the Arabic countries, but did not transmit very well into the Western societies, mostly because of the sway of the Romans, because this did not sync well with their system. And so it wasn't until 1202 that the mathematician that would become known as Fibonacci published the Liber Abaci, the Book of Computations. And in this publication, we again see in Europe that 0 is a number, and it can be used in computations, and 0 is the number that when we add it to any other number, it does not change that number.